research page. This is a talk I gave at AICHE a few days ago in Orlando at the Fall 2023 meeting. It was a keynote lecture designed to be kind of a perspective on data science and machine learning approaches in catalysis. And in describing the talk to a friend, Victor Zavala, and I told him what I was going to try to do with kind of 3 vignettes of different approaches and ideas in data science and machine learning. He said it sounded kind of like the ugly, the bad, and the good. And so there's a subtitle on this talk along those lines that'll become kind of apparent. Now this view, this perspective is pretty biased by the work we've been doing in my group for the last five or more years. And it covers a bunch of different areas in experimentation and molecular simulation and scientific programming. But all of them are related to data science and machine learning. And so the purpose of this talk is really to give you these 3 different perspectives on what we've done, what we've learned, and what kinds of things are possible when you think broadly about data science and machine learning. Okay, so let's get into the first session, or the first piece. This is a project I worked on with Stefan Bernhard in chemistry at CMU, Zach Ulyssi, a former colleague who's now at Meta, and Jill Millstone, who's in chemistry at the University of Pittsburgh. So let me lay out the dream, because I think this is a common dream. I see a lot. I even still have this dream that we can do this data-directed, machine learning augmented, or accelerated synthesis of materials and discover new catalysts or new other things. So Stefan's group has an amazing photochemical reactor that is based on this 96-well platform. You can fill the wells with different materials, different metal salts, solvents, fuels, photosensitizers, ligands, etc. And then when you shine light on it, it generates hydrogen. And where you see these black circles, that's where hydrogen has been produced. And where you see light gray or white, that's where hydrogen is not produced. So we can, in one day, one 10 to 15 hour experiment, screen 96 different compositions or synthesis conditions and see which ones make hydrogen. So our challenge here was we had 20 or 30 metal salts that we could do. That makes 190 binary pairs, nearly uncountable composition variation if you look at different concentrations and different fuels and different other kinds of conditions. And so what we thought is we would be able to run this cycle where we could, say, sample this binary pair systems down here, make the measurements, turn the measurements into data, and then use the data to generate a machine learning model, and then from those predict via the color where the best materials would be. And so that would help us speed up the discovery of new materials or new understanding. So that was our dream, and that's what we set out to do about, seems like 4 or 5 years ago now, to do that. Now, I'll just cut to the chase. It did not work the way we imagined. We did do tens of thousands of experiments, and we did learn a lot of interesting things, but it didn't happen because of that machine learning closed loop cycle. And I'll talk a little bit about why that is. The most important reason, I think, was this paper that we wrote at the very end that showed us that what happens in that system is metal nanoparticles get nucleated, and then they grow over time. You get a distribution of sizes and compositions with time. And looking back 5 years later now, it's pretty clear there was kind of no chance for machine learning to work across that composition space. Among the things we learned besides this, sometimes we made particles that crashed out of solution and then they weren't active. Sometimes we didn't make particles and they weren't active. Sometimes we made particles that weren't active. And so looking back, there's kind of no way we could get a single machine learning model across all of those metals, across all of those variations to be predictive in that. Nevertheless, because it didn't work, we spent a lot of time trying to understand why it didn't work, and that led to this paper, which is a very interesting piece of work on nucleation of metal nanoparticles via this photocatalytic reduction, and we learned a tremendous amount about nanoparticle synthesis in doing that. Now, what we also learned is, although machine learning didn't help us a whole lot, a very traditional design of experiments was super effective. So I mentioned we had particles that would grow and then crash out of solution and sit on the bottom of the wells. Those particles weren't very active, and it's no surprise to people that do nanoparticle synthesis that precipitation can occur. But in this high throughput system, you have to have a way to know when something fails, why does it fail? And then if you can prevent that failure, you can still learn some new things. So we had to add some ligands into the synthesis to stabilize these particles. And to find the optimal conditions, we really fell back on this very traditional, conventional design of experiment, variations of Box-Banken designs or factorial designs, where we could take a specific plate, map out some degrees of freedom that we wanted to do experiments on, do those experiments. The experiments for each well, we monitor the darkness of each well as a function of time. That gets converted into these kinetic traces down here, and we can take all of these kinetic traces and map out what the activity across the plate is. And then once we know that, we can zoom in on where the best material, where the most active conditions are, and from there we can do detailed studies like TEM and XRD and XPS. So we don't want to do all of these expensive detailed studies on all of the materials in every well. It's just too expensive, and not all of them are interesting. You know, this region over here is not especially interesting because nothing interesting happens. So we wrote 2 papers on this where we were able to show that we could stabilize the particles. You can see up here, if we don't have ligand, they die very quickly. And if you do add ligand, then we get good activity that's stable over many cycles. Again, this is the kind of thing where machine learning can't tell the difference between these kinds of things. In both cases, this would be palladium. One of them has a ligand and one of them doesn't. And we just don't have a capability of building machine learning models that can differentiate these without knowing about the ligand that's in there. And there are many ligands that you can choose, so that increases the dimensionality of this problem. All right, so traditional design of experiments was very effective in this work. You can substitute in these traditional models, just use linear surface response type polynomial models. You can substitute in more nonlinear models using machine learning within a plate, but we were not able to go across compositions and expand that work. This is a little bit, I don't know if if embarrassing is quite the right word, but you know, having spent my career doing DFT and studying model systems with DFT, it's fair to say here that the DFT connection was less strong than we hoped. So we anticipated we would be able to screen through all of the binary and ternary kinds of alloy space using hydrogen adsorption energies to screen out and find good materials. But what we found in practice was that didn't lead us directly to the best materials, and I'll show you in a minute. Had we stuck with that, we would have missed important materials as well. So we did do a lot of DFT calculations. We did screen via machine learning models a very large composition space. And what we found in this work is that the adsorption energies were just not enough to predict hydrogen evolution. There are other factors that have to be considered, you know, including where the particles made, what is the size distribution, what kinds of active sites are available, and whether or not segregation or other kinds of things might occur in composition in bimetallic or higher compositions. So we did discover that, you know, it was kind of necessary but not sufficient, and it could reduce the search space by, you know, maybe half, but that space was still very large, and so DFT alone wasn't actually enough in this. Now, another wrinkle we learned along the way in some of the previous work that I just described on the ligands, when we make a particle that we call iron, it turns out it wasn't actually an iron nanoparticle, but an iron sulfide nanoparticle. And another one we looked at with nickel turned out to not be a metallic nickel, but really a nickel oxide or nickel hydroxide type particle. So that's another reason why the DFT connection is less strong than we hoped for, is that across the metals, we don't always make metallic particles, but that is always what we calculated in this high throughput screening methodology here. So across the whole space, we weren't able to model exactly the same thing that got made, and that made the connection between them a little, well, certainly less strong than we anticipated. Okay, we did learn some other kind of positive things by being able to work on the high throughput system. We were able to not only screen lots of metal combinations, but we could look at lots of different fuels for making hydrogen. The goal of this project was looking at oxygenates, things that are potentially biorenewable, like glycerin, ethanol, other kinds of things that are in here. And we were able to screen a lot of different fuels, potential hydrogen sources, lots of different photosensitizers. And in this figure, anything you see that is white or yellow or orange means that we were able to make a lot of hydrogen from it. And then anything that's black are combinations that weren't very good. So what this tells us is there's a lot of opportunity for making hydrogen from these hydrogen sources, and that's pretty exciting. That was the whole point of doing this work. The last thing I'll talk about in this part of the talk is not to give up on serendipity. So one of the best materials we found that wasn't predicted by theory was a copper, ruthenium, iron immiscible metal system. Now this would have never been predicted by theory because these are immiscible metals. They don't form alloys. And so we didn't even try to calculate what would the hydrogen activity on those systems be. And when we did this work in this paper down here, we found that copper and ruthenium were not good catalysts at all. They're hardly active on their own, but together they form a pretty good catalyst. And this ternary of copper, ruthenium, iron shows many points in this ternary space that are among the best we ever saw of any catalyst in all of the thousands of systems that we did. Now this one I call serendipity for a couple of reasons. We didn't do any kind of calculations on this system, again, because we didn't expect it to form an alloy, so what would you even calculate? But also because it's experimentally known they're immiscible, you might not be inclined to even try the experiment because there's no reason to think it should make a good catalyst. But we did these experiments kind of for fun, and we found that we got this very interesting synergy in here. And we see that we down here you see we have like a broad range of particle sizes and distributions in composition, and so it's not at all clear. We don't make a single material that's all made in situ, so it's not at all clear why it's better, but it's unambiguously better, and that's an exciting finding we would not have found if we were trying to synthesize particles, characterize, and then measure. So that's a feature of this particular approach. So I'll wrap up this part of the talk on summary thoughts that complex systems like this one, they are complex. It is not likely we're just going to DFT, machine learn our way through them. In this case, we went in a data-rich perspective where we just did a lot of experiments to see what is the landscape and see where the interesting places are. It would be nice if we could do something that was physics inspired, but in this case we have photons, we have hydrogen reduction, metal salt reduction, fuel oxidation, a lot of things happening that we don't understand well enough to write models for. But a critical point that I want to make here is that we learned a lot by trying this. And we learned a lot by trying to understand why it didn't work. And the critical point here is to get a bunch of smart people in a room thinking really hard about a problem, talking about solutions, talking about what might happen, and then designing experiments and paths forward to do it. So I think that's a critical point to think about if you are trying to combine machine learning and experimentation. It's going to involve multiple groups, and you really need these two groups talking to each other to solve your problem. Okay, part 2 is a different point of view. So that last one was really about data science, a little bit on machine learning, and how we tried to apply it in a way that didn't work. That was maybe the ugly in the talk, although good things came out of it anyway. Let me switch to a different way of thinking about machine learning and molecular simulation. So my group has been doing density functional theory calculations for maybe more than 20 years now, and they're quantum chemical semi-first principles approach to calculating atomic properties. You can kind of loosely think of them as a way of practically solving the Schrodinger equation. And the only issue with them is we find they're very expensive to do, and that limits us to, hundreds to thousands of atoms. And even though we can do quite large number of calculations now, the number might be in the thousands to 10,000s for regular things, and that's not adequate for doing something like Monte Carlo or molecular dynamics in general. So when we look at molecular simulation in general, we're solving or evaluating some equations that tell us about properties of materials at some scale along here, and we should think about where these equations come from. Now, we have two options in a way. One is density functional theory over here. This is a picture of Pittsburgh. Carnegie Mellon, where I am, is sort of in the back. This is the point where we have two rivers that come together. Over on the left side, I characterize the state of force fields. These have been around for maybe 100 years. They're very well developed, and there's not a whole lot of green space, room for further development over here. And I feel like that field is slowing down in ability to accurately simulate materials across the board in that space. Over here is Mount Washington, very steep, but lots of space to move. But it's very difficult to build new DFT functionals, and it's very expensive to do that. So I've been working in this middle area where we try to bridge these two fields with something I call machine learned potentials. I didn't make up that name, but it's been around for also about 20 years, and it's been continuously evolving in a way that we can use DFT for training data and build a model that is almost as fast as force fields and useful those ways. Okay, so that's what I'll talk about for the next part. I do a lot of the current generation of this work is in collaboration with Meta and in a project that Zach Ulysses started called the Open Catalyst Project. And this is a project where we use graph neural networks to take an atomic system, represent it as a graph, build a set of features, and then train those features to predict properties like energy, forces. I'll talk about electron densities and other properties as well. So this is really a state-of-the-art set of models. It's been trained on millions of DFT calculations on different slabs, different surfaces, different adsorbates, covering metals, intermetallics, ionic compounds, etc. And there's a second version, OC22, that adds oxides to the database. So these are now pre-trained checkpoint models that you can download and use for a variety of applications, and I'll tell you about a couple of them here. So the first thing maybe not the first thing, one of many things we can do is use these to accelerate molecular simulations. So we can speed up DFT calculations here, and that will allow us to do less DFT because we can use these machine learned potentials as surrogate models for the forces and pre-relax or take some of the work off of DFT for doing that. We can also use this for nudged elastic band calculation, so we can use these pre-trained models to estimate what a trajectory along a minimum energy path might be, and that works very well also. And sometimes you can use it for screening materials and then only using the most relevant ones that come out of that for your DFT budget. The second thing that we've done recently is show that we can use these graph models for predicting magnetic properties. So the previous example was all about energy and forces, but other properties work as well. So we can take a graph of some atomic system here, and then we train a graph neural network model to do two things. First, to classify each atom into magnetic and non-magnetic. So that's these blue blue and red points here. And then once we have this embedding vector here for the magnetic ones, we can use that for predicting the magnetic moments of each atom. So this allows us to get better initial guesses when we do our DFT calculations to initialize it and find good magnetic ground states. And I think as we move forward, we'll have even better models where the magnetic moments are actually degrees of freedom for the inputs, and we'll be able to directly optimize magnetic properties. Another exciting direction that we can do is predicting electron density. So you can think of energies as predicting a scalar, forces as predicting a vector. Electron density is really predicting like a tensor, a second order or a 3D array of grid points. Now we also use the OCP models for this, and we make an augmented graph where we might have, say, these platinum chemical atoms, and then we have these yellow probe points. And we still use the graph neural network capability to build a model for what is the electron density at each of these yellow probe points. And then once we do the training, we can take a new system and calculate or predict what the electron density is. Now that has a lot of interesting applications moving forward, because almost every property is derived from the ground state electron density. So we can take that density and decompose it into Bader charges, or calculate dipole moments, or even use it as a better initial guess than superposition of atomic charge densities in DFT calculations. This paper is out on arXiv. You can find it in the video comments, and was recently accepted for publication. So it should be out pretty soon. All right, you can learn to use OCP yourself. There is a tutorial that we wrote and gave as a tutorial at the ACS meeting in the summer of 2023. One of the applications we used in there was to take the data from this paper, where they had lots of A3B alloy surfaces, and they wanted to screen the hydrogen and nitrogen adsorption energies for things related to ammonia. And then we could classify which ones are good for ammonia reduction or nitrogen reduction down here, and which ones are predominantly hydrogen evolution. So this involved something like 19 or 20 metal alloy surfaces. Then you take those and generate all the different adsorbate placements to find the most stable site, and then from that you can generate these correlations. So it turned out to be roughly 400-ish DFT calculations that was in the original paper that would have taken several weeks to do. We were able to reproduce the results with OCP in about an hour during the tutorial. So hundreds of adsorbate placements, hundreds of relaxations, all took about an hour to do with this method. So lots of exciting opportunities in this space for doing new things that haven't been possible before. All right, the last part of the talk is really having seen, there's data science we can apply to experiments. There are state-of-the-art machine learning methods that we can use in molecular simulation. We can take a step back and ask, why is that even possible today? And what else could we do besides those two things? And so this last part of the talk is really recognizing what makes this possible, and then talking about this new paradigm of scientific programming that is changing what else we can do with data science and machine learning ideas. So my point of view is machine learning is just a new way for model building. It's taken a few decades of research that have converged with some decades of software and hardware development. But the result is that today we can build these models on your laptop, in many cases train them on a laptop or desktop, and it no longer requires the most specialized knowledge that was required before. So that is starting to have some changes, and I'll show you exactly what that means. So the biggest change that I've seen in the last 5 years is the development of automatic differentiation as a commodity programming tool. Automatic differentiation has been around for a long time, but it was kind of hidden deep in compiled libraries with Fortran or C, and the level of skill required to use them was just beyond what most of us generally have. Today, it's a common feature in Python, in Julia, and other programming languages, and it's the most common feature in machine learning frameworks. So let's talk about automatic differentiation for a minute. What is it? It is an approach to compute derivatives of programs. If you have an equation, you can probably derive a derivative and then implement that derivative and hard code it into some optimization routine. That's how neural networks used to be 5-10 years ago. Today, that's not what happens. You write a program that expresses the model, the neural network, whatever it is, and then use automatic differentiation to get the derivative for that. Now, it is not numerical differentiation. It is not like a finite difference approach where you have to check for convergence and check for stability. It's also not symbolic differentiation. That's something that Mathematica or Maple would do, and those are not practical for real machine learning problems because they generate maybe hundreds of pages of code that's not optimized. What it is an application of the chain rule to a program. And so once you write your program, it's aware of all the elementary derivatives, and it can work its way through your program and just take the derivative at each step and accumulate the derivative and evaluate it at the point that you're asking for. So it's not a standard feature of most languages, but it is a standard feature of all modern machine learning frameworks, PyTorch, JAX, TensorFlow, etc. And because we can now write programs with derivatives, we can do a lot of new things, and it has a lot of roles in molecular simulation and in science. So I'm going to tell you about this paper. This is a degree of rate control that we worked out using automatic differentiation. All right, so the degree of rate control is the most modern idea of what is the rate determining step. So here is a 17-step partial oxidation of propylene, and we, in the paper we got this table from. There are all these rate constants, activation energies, and we might like to build a mole balance on each one of these species and then use that to calculate the overall rate. And then the critical point is which step is kinetically relevant or rate determining. So how do we find that step? Because that's the thing we want to change in any catalyst to speed up the rate. Now, a conventional way of thinking about this would just be to find the biggest barrier, so like 166 or 131. These are among the highest barriers, 135. But this approach doesn't work super well because there is also this pre-exponential factor over here, and you see some orders of magnitude variation. So what the degree of rate control does is let us do something like a sensitivity analysis, which is to say, if I could change some of these parameters, which one changes the rate the most? So that's the idea of the degree of rate control. It is a form of sensitivity analysis. We look at partial derivatives of the log rate versus the some of those parameters that I just showed you, and then we want to know which one. This is a normalized sensitivity analysis, so this typically will vary like -1 to 1, and we want to see which of these parameters is the most relevant. Now, this is normally done when you have an analytical expression for the rate. So this is the derivative we need. Even for something simple like this A goes to B, or A plus B goes to C, you see this very, very complex, I think it's complex, rate expression, and then you have to take the derivative of this expression to get the degree of rate control. Now, it is just an application of the chain rule, all the way through, but it's moderately tedious to do, and even if you do it correctly, you then have to implement it correctly, and even if you do that, it only works when you have these analytical rate expressions. If you don't have an analytical rate expression, then we have historically been forced to use finite differences, and I'll show you those are difficult to use, less accurate, and not stable. All right, so that's what I show here. You can read the paper for like all the details, but it turns out that analytical or automatic differentiation is equivalent to an analytical expression because we evaluate the chain rule at every step in your program. There's no approximation at all, and it's faster and more precise. So I show in here comparison of the in black automatic differentiation. You see in every case here it's smooth. And then for the finite differences, we can check, we have to check a range of finite difference sizes. If you make it too large, you get instability. If you make it too small, you get instability because of things like rounding errors and float tolerances. And so you have to do kind of 3 steps to figure out where's the right balance to get something that's accurate. So it takes longer and it's more tedious to do. But the automatic differentiation comes out right away. It's smooth and accurate. And so we can see in these cases, this reaction number 4 has very limited DRC. It's not relevant at all. This one goes up to 1, so reaction 14 is very relevant. Reaction 3 is less relevant, but not irrelevant. And reaction 17 is also less relevant, but not irrelevant. So we can do this for all of the reactions, for all of those parameters, and find out. And this is really a way of writing scientific programs with derivatives that wasn't possible before. All right, so I'll conclude there. It's probably hitting a half hour or so. And say we used automatic differentiation. It was implemented in Julia for this work, but now it's possible in Python using JAX or other tools. The automatic differentiation is faster, it's more accurate than finite difference approximations, and it allows us to do things in systems where no analytical solution for the overall rate exists. Those derivatives we got by taking the mole balance, integrating them forward, and then taking the derivative backwards through a numerical integration term. So that's a pretty amazing capability that exists. You can find these in all kinds of implementations, Julia, PyTorch, TensorFlow, etc. And I think it's changing the way we write programs now in molecular simulation. If we have an energy model, we take the derivative to get forces. In optimization, we can accelerate optimizations of objective functions by using automatic differentiation to get the derivatives of them. Here I showed you we can write a program to do a kinetic simulation and then do the sensitivity analysis for degree of rate control in an automated way. So it's changing how we think about doing this, and it's going to continue changing as these tools evolve. All right, automatic differentiation is kind of new. I wrote this book on it. You can find at pointbreezepubs.gumroad.com, so you can learn about using automatic differentiation there as well. Okay, and I'll finish here. The talk today had these 3 parts, one on data science and machine learning with high-throughput experimentation, where it wasn't as successful as we thought, but we learned a lot of things anyway, and if we were to do it again, we might find a different approach that leads us in a more productive direction. The second part was on large graph neural network machine learned potentials. Those are amazing today. They span like 55 elements. They work across a broad range of systems and are enabling a lot of different kinds of simulation methods that weren't possible before. And then the last part on automatic differentiation got us to an application that is a result of those underlying frameworks that the first 2 things laid on. Now, there's still a lot more. People are using data science, machine learning in image recognition or image analysis. They're also applying it in natural language tools to read the scientific literature on catalysis. There's a whole new field of generative methods that people are interested in that I wasn't able to touch on here. But what that means is that there are lots of different ways data science and machine learning are impacting catalysis today. And if you're not learning about it yet, it's probably time to find where it is going to have an impact on your work. All right, that's all. Thanks for listening, and I hope you Hope you learned some new things and found something interesting in this talk. See you next time.